Alright, I want to show you guys some new progress on the new transceiver, the BITX DIGI-TIA. It's called Digi because Pete Giuliano has obligated me to use an SI5351 chip for VFO and BFO signal generation, TIA for Termination Insensitive Amplifier, TIA. Here is the board. Pete gave me the board. It's milled on his CNC that he has at home in his Newbury Park, California lab. Very, very cool. I kind of like it better than even Manhattan construction. I have the receive halves of two of the TIA amplifiers built. The TIA amplifier, the Termination Insensitive Amplifier, was designed by Wes Hayward and Bob Kopchi back in 2009. It is in response to a need that was kind of generated by the advent of the BITX series of transceivers. The problem is that you need amplifiers that are going to always present the same impedance load to the crystal filter no matter which way the filter is working, forward or backwards, receive or transmit. And a lot of amplifier designs, the input impedance will be affected by the whatever's hanging off the other end. They are not, in other words, termination insensitive. They're termination sensitive or transparent. This design, however, always presents a 50 ohm load at both ends of the amplifier, which is really very cool and very useful. I'm using here a Yaesu XF90A crystal filter. It's an SSB filter at 9 megahertz. Steve Snort-Rosen-Smith gave it to me a while back, and I'm finally able to use it in a circuit. It needs 500 ohms. The amplifiers present 50 ohms, so I built two little 10-to-1 impedance ratio transformers, and they are making the necessary impedance transformation. Let's see how it works. What I have set up here is a signal generator, and it is an 809850 chip with an Arduino, and I have it going into the first amplifier, through the filter, and out. Now I have this thing tuned up above the passband, so we'll move down in 100 hertz increments, and as we go I've recorded the data here. It looks tedious, but it's not. It's very easy. Watch the scope as we move. We're above the passband and we're getting 0 volts through. And as we move down closer to the passband, all of a sudden there you go, there's 20 millivolts. You're starting to see signal coming through. Move it down again, more, again, moving it. At each point I'm recording here the value. And you can see as we move into the passband it starts to become quite strong and quite steady. And that's what you want. Now, there'll be some variation in the signal strength as you move through the passband. That's ripple. You want to keep that to a minimum. I mean, there'll always be a little bit, but this actually worked out quite well. So now I'm down. We're kind of in the middle of the passband now. And you'll see it moves a little bit as I change, but not much. Going along quite nicely. Now, as we get down to the lower end of the passband, you'll start to see the signal decline. There we go, it's starting to drop. Every time I move by 100 hertz, it's dropping more, dropping more, dropping more, dropping more, dropping more, dropping more. There we go, we're pretty much gone. We're out of the passband. I could tell from the eyeballing it looked pretty good, but when I plotted these numbers here, I looked again, I could see it's good, but then I went over to an Excel spreadsheet, plugged in all these numbers, and converted the voltage values to dB. I picked the high point. I mean, I think the voltage peak was 386 millivolts. That became the high point, and everything else was plotted as dB down from that peak. Then I asked the Excel spreadsheet to put it on a graph, and here's the graph. You can see, quite nice. This is dB down. There's a little bit of ripple in the passband, but not much, not enough to worry about. And the bandwidth comes out, as predicted, about 2.5 kilohertz at 6 dB down. So this shows what you could do with some real simple test gear, and I'm quite pleased with it. Now I'll go on and build the next stages in this rig, and hopefully we'll have it on 40 meters and possibly other bands here within the next few weeks. Again, one of the most fun parts is doing this with the collaboration and input and ideas and parts from friends. So thanks to Steve Snort-Rosen-Smith, to Pete Giuliano, to Wes Hayward, Bob Kopchi, and Ashar Farhan for for all the great ideas and parts that are going into this this little rig. Thanks a lot, guys.